everyone, welcome to this newest video. My name is Johan and together with me is a very special guest. It's Niels Hagoort, a tech marketing architect at VMware. And today we're going to talk about something that's really dear to us. It's graphical acceleration, a comparison with CPUs, and a topic that Niels has blogged about in the last couple of months. And something that's dear to me from a graphical acceleration perspective. So I did a lot of stuff with GPUs. You may have remembered the race car simulator, but also some vGPU stuff. And Niels, you're like a true specialist on resources and vSphere stuff, right?
Well, I try to be.
Yeah.
But yeah, it is an interesting topic for sure. Yeah.
Cool. So. Right, so CPUs and GPUs. We're going to talk about applications.
Yeah, definitely. So it's more about the applications that could benefit from a GPU.
Yeah.
And GPUs in itself, I think it's fairly new, right? Because we used to, and you know this, right? We used to use GPUs for graphics acceleration in virtual desktops, for example. And nowadays we see an whole shift on GPUs being used for machine learning, artificial intelligence, everything that comes with it.
Right.
Yeah.
Cool. So so we're going to talk about apps. We're going to talk about the difference in architectures and some of the considerations you need to take into account when using GPUs for some of your specific applications that could benefit from it. So, how would you like to start?
Well, I think it is interesting to take a look at why you actually need GPUs, right? Because we have CPUs in our common x86 hosts, but there are some major differences between a CPU and a GPU. So let us start with just a high-level overview of what a CPU architecture looks like, right? And the main difference, I guess, is that a CPU package, if you have a CPU package and a GPU package, and again, this is just a really high overview, right? The biggest difference is that when you have a CPU package, you have, depending on make and model, obviously, you have up to 28 or 32 cores within one package. So most of the time we see a dual socket layout in a common host. But that's the main difference, because if you look at a GPU, you will notice that it consists of a lot of cores. And that's the basic difference, and so on, so on. So that's the basic difference between a CPU and a GPU.
So it's the number of cores.
It's the number of cores, and well, it's not only that, it's because of the nature of a CPU is all about being optimized for latency. So latency sensitive applications, right? Where a GPU is more about throughput. And this is, well, we can see that throughput because we have an X number of cores, and I do not have the exact number, maybe you do, but a flagship offering of Nvidia consists of like 5,000 plus cores.
So take like a Tesla P4 or Tesla T4, they have up to almost 4,000 CUDA cores.
Yeah, well, there you go, right? Yeah. And we'll talk a little bit about that later on. Well, what we can do is we can zoom in on a CPU architecture, just a high-level overview and why it is built for latency and as low as possible latency. Yeah. And what we will do next is we can go to the GPU architecture and have a look on why it is optimized for throughput and large computations, because that's basically it, right? Okay. So when we look at a CPU, and we'll zoom in on a specific CPU core, right? So we just explained that a CPU has like 30-ish cores.
Yeah.
When we look at a core of a CPU, what we notice is that we have both a layer 1 cache for data And we have instruction cache. Now, those are dedicated per core within the CPU. What we also have is, what we also have is a dedicated layer 2 core, layer 2 cache. Now that cache, again, depending on make and model, can be up to like 2 megabytes, which is pretty large for a modern CPU. And what we have next is the last layer cache, or layer 3 cache. Now that is shared among cores. So we have even
among
more cores,
all cores.
among all cores within the CPU package.
Yeah.
Now, to show you that latency, it is important for a core to quickly have memory access, if you will. So what it will do, it will fetch data from the layer 1 cache. If it's not available in there, it will hop to the layer 2 cache, layer 3 cache. And if it's not in the last level cache or the layer 3 cache, then it will go ahead and it will talk to the memory controller. And that is connected to the actual global memory.
Right.
And that's your DRAM, right? So it is all about quick memory access and being able to in a sequential way, do calculations. Now
That's important, sequential way.
Yes, that's key. Because that's perfect for your common IT applications, right? But when we are talking machine learning, artificial intelligence, large data sets and computations on those data sets, we need throughput, we need parallelism.
Yeah.
And a CPU is not the perfect architecture to do so. So let's have a closer look at GPU architectures. Another important thing to note with a CPU core is that it's scheduled per core, right? And that is interesting when you have a look at a GPU package.
Yeah.
Because a GPU package consists of many processing clusters. And within these processing clusters, we have so-called streaming multiprocessors. And a streaming multiprocessor, that is where the actual CUDA cores in this example reside. Yes, exactly. So remember we talked about the number of CUDA cores within a GPU. It's mostly in the thousands depending on make and model.
Yeah.
So the biggest difference with this is that, and this, just to empathize, this is just one processing cluster, right?
Yeah.
A common GPU consists of
multiple of them.
Yeah, up to 30, 40, I believe. Yeah. Now, when you have computations on a large data set, that is scheduled on a processing cluster, because one processing cluster can also have multiple streaming multiprocessors in it. So if you schedule on a processing cluster, it will then go ahead and schedule on multiple SMs, multiple streaming multiprocessors. And that's parallelism for you, because now we have a lot of cores doing computations for you, and by doing so, being able to provide the throughput you need for those applications that you run on it.
Right.
So that's the main difference between a CPU and a GPU architecture. Now we talked about memory access with a CPU package. So if you look at the GPU architecture, what we see is that we have a layer 1 cache that's residing on the processing cluster and per streaming multiprocessor. But that's a fairly small cache size, because when we put a GPU to work and we have a job for it, a machine learning job for instance, it's not really about memory access. Yes, we do have dedicated memory per processing cluster, but it's more about the calculations and the computations in the cores itself. So by a GPU being busy, it kind of hides the fact that CPU or memory latency is slightly higher than when talking in CPU architectures. So what we see, we have a layer 1 cache and we have a shared layer 2 cache. And again, we have multiple processing cores, right? And on this side as well. And when data is not fetched in either layer 1, layer 2 cache, it will then go ahead and go to the memory controller and to the memory, to the global memory, which is, if I remember it correct,
is DDR5.
Yes,
yeah, so
exactly.
To emphasize, this is frame buffer memory. So it's the physical memory on a GPU. It's not your RAM memory in your host. And that's one of the differences between GPUs and CPUs as well. The memory used in a GPU is much faster because it's DDR5 memory instead of DDR4, which is common in hosts from nowadays.
Yes, that's correct. Okay, so now we have the GPU, the CPU. We think it's a really good idea moving forward when looking into machine learning applications that you utilize a GPU. And what we can do now, and we can talk a little bit about how vSphere supports GPUs, right?
Sure, yeah, let's do that. Okay, so next let's talk about how vSphere is able to interact with a GPU.
Yeah, that's a good idea. So we have multiple options for you to provide GPU functionality to your VM. And it's more of the choice, what do you want to do and what is required from a app's point of view, right? So if you talk to a data scientist, and you talk to multiple data scientists yourself as well, they would probably go ahead and ask for a full GPU that could be used for that specific workload.
Yeah.
So we have a dedicated GPU.
Right. So in this case, the GPU is directly attached to a VM.
Yes. So it's a one-on-one relationship, right?
Right.
So, but that GPU is gone. You can only use it with one VM.
It's fully allocated.
Yes.
Yeah.
So the other option we have is to have multiple GPUs for a VM.
Right.
So that's like a 2-to-1, whatever is required.
So possibly multiple GPU cards, so physical GPUs with frame buffer allocated to a single VM.
That's correct, yeah. I think it's a rather expensive solution.
Yeah.
So what we also have is what we are doing with virtualization, right? Is that we have one GPU and many VMs.
Right.
So this is what we do with compute as well. So we slice up the physical hardware and we have dedicated cores, GPU cores for a specific VM.
Right, and we need Nvidia Grid, vGPU, in order to use that. So the physical frame buffer of a GPU will be sliced depending on the allocation profile that you select for the VM. It will not be overcommitted. So it's like RAM, because your RAM best practices in a host, you won't overcommit RAM. In case of a GPU, you aren't even able to overcommit RAM, but the GPU itself, so the cores, will be overcommitted based on a GPU scheduler, like you would do with vSphere as well.
Yeah, exactly. So when we look at the various options we can provide to our customers, when we are talking dedicated GPU, we have the option to go with direct path I/O.
Right.
But like we know, that comes with a lot of constraints when you look at vSphere features, like HA, vMotion. We can also...
So in this case, the hardware itself is directly linked to the VM.
Yes,
so
there's
VM,
no scheduling between.
No.
It's just a one-on-one relationship and just a complete pass-through.
Yeah.
to the hardware itself. We also have Nvidia Grid that can provide this functionality for us. When we look at multiple GPUs that we can assign to one single VM, we can again do that with Direct Path I/O. And we can use another third-party solution that is Bitfusion FlexDirect. But, like we said before, we would like to have one physical device, chop it up, and be able to let multiple VMs take benefit of that physical hardware piece. And that's obviously when the sharing comes into play. And again, we have solutions like Nvidia Grid that supports that.
Yeah, and this will offer you basically
FlexDirect.
Much more flexibility.
Yes.
Right.
So, can you tell us a little bit more about Nvidia Grid, because it introduces a new type of scheduling that is
absolutely
completely separate to the VM kernel scheduling?
Yeah, absolutely. So Nvidia Grid has its own GPU scheduler which sits between the VM and the actual GPU. So let's draw a VM here. The VM has a vGPU profile. And the vGPU profile obviously is linked to the actual GPU. There is, like mentioned, a scheduler between it. And the scheduler will make sure that every resource that's required by the actual VM, or the vGPU in this case, is being scheduled based on what the VM requires. So there are three types of schedulers. One being a fixed share scheduler. So every VM that has the possibility to run a vGPU profile gets its own fixed share of a physical GPU. Well, the fixed scheduler will be used in a, for instance, DaaS point of view. So if you buy a physical desktop or a virtual desktop from the cloud, and you pay for that GPU, you will get that GPU. So you have paid for it, so it's yours. There are two other types of schedulers, one being best effort and one being equal share. In case of the best effort, like it says, if your GPU, your virtual GPU requires a bit of computation, it will get that. But as soon as you don't require that, you will be put out of the scheduler, and other VMs will get that. And the GPU scheduler will try to do its best for you, for your VM to calculate stuff. This one isn't really suitable for CUDA-related workloads, because in case of a CUDA-related workload or a HPC or computational workload, you want the GPU to calculate your resources based on the fact that you need it directly. So there's a third scheduler called the equal share scheduler. Equal. And what the equal share scheduler does is, let's take a diagram. If you have 3 VMs, for instance, that need resources, VM1, VM2, and VM3 will have their equal share of the GPU. And please note that this type of scheduler will enable your VM to get resources if it is powered on. So powered off VMs won't allocate anything. And that's the main difference between this scheduler and the fixed share scheduler. The fixed share scheduler will allocate your VM resources, also if the VM is not powered on. Right, and so this scheduler will make sure that if a CUDA workload or a computational workload is started, that it will always get resources from the GPU when required. Please also note that there are mainly currently 2 types of GPUs that are available in the market. One being everything that is newer than Maxwell. So this is newer or equal to Tesla. and everything that's older. So that's Maxwell and everything prior to Maxwell. So Maxwell GPUs have two types of modes, one being graphics mode and one being computational mode. These GPUs aren't suitable to be used in a mixed environment. So if you have a GPU environment in which you have many VMs to a single GPU, you'll always be limited to have that physical card being used for a single use. So either multiple computational types of VMs or multiple graphics types of VMs. The two cards that are still available, or one at least, is the M10. So M10, a Tesla M10, which is mostly used for high density graphical use cases, so VDI, and the other one being the M60, which is might still be available. I'm not really sure, but this card is suitable for both graphical and computation. But again, you need to configure the card to a specific use. All other cards are able to mix both computational as well as graphical workloads on a single card.
Yeah, that's good information. So not every GPU is usable for doing computations, machine learning, etc.
Well, they are, but they aren't in a mixed environment.
Oh, sure, gotcha. Yeah.
Yeah.
Okay.
Awesome.
So when we look at how vSphere supports GPUs, there's one thing I want to mention is that, so we used to have VM portability by using suspend and resume, right? So we can send a signal to the GPU that it suspend that specific workload on the GPU, move the VM to a different host and resume again. We now also have vMotion support for vGPU enabled VMs. Yeah. So that's good to know as well.
And specifically for computational workloads that benefit from a GPU, this is key because you want, if you start up a computational workload, for instance, a research task by TensorFlow that could easily take up 5 to 6 hours to a whole weekend even, you don't want that VM to be interrupted because of maintenance. And vMotion, like years ago, was intentionally or maybe co-intentionally created to avoid downtime during maintenance and being able to take out hardware of your cluster and your VM still being available. So vGPU vMotion from a computational perspective is great because those data scientists and those researchers, they don't want that downtime, and they want to guarantee that their tasks are still running in the weekend or during maintenance windows. Please note that a vMotion has, in the current version, so vSphere 6.7 U1, has a slight delay when you move a VM from one host to the other. Depending on the size of the frame buffer of the physical video memory, that freeze could take like a second to a couple of seconds even. And from a VDI perspective, that's okay. You need to be aware that freeze occurs, but from a computational perspective, a data scientist won't notice that freeze. And we'll see what happens in the future in terms of that freeze. Maybe something will change, maybe not, but for now, it's okay, and it's a big advantage from a maintenance perspective. Right, applications.
Yes. So if we look at your typical IT application, it's fairly simple, right? So we have an application running on a VM.
And it doesn't really matter if this is like a 3-tier application or a legacy application in general. It can be any application, right?
Yes, that's the beauty of VMware, right? And we can use any application which go to the VM kernel all the way down to the CPU. So there's no intelligence required within the application to use the kernel and the hardware bits underneath it. So maybe you can tell something more about how that works with the GPU. Is there
sure.
a certain layer of intelligence required from the application?
Yeah, so like Niels, let's draw the application itself. Let's draw the VM a little bit different. So this is a VM, and here still is a bit of kernel, and a CPU.
And with kernel, you're still talking about the ESXi VM kernel.
Absolutely, because every application will still need access to a CPU and still access to a RAM in order to compute stuff. Where it is different is that, again, we have the vGPU profile, and in order to use the vGPU profile or GPU in general within any machine, either a VM or a physical machine, you need to leverage a framework such as CUDA or Tensor or any other framework that's able to compute stuff through a GPU. So this is really important. Applications that aren't able to use a framework like this aren't able to calculate things over a GPU. Because the GPU itself is, the vGPU profile will talk to the scheduler, and the GPU next to the CPU. Again, very important. Both of those resources are necessary for an application to run, but this is really important. The thing is, and this makes the GPU architecture and Nvidia's framework for leveraging GPUs in a virtual environment maybe even more powerful, because what you could do is not only have VMs running on that platform, you could also use something like Docker. Please note that there is a specific Docker version for Nvidia, and I think it's called Nvidia Docker. And you could also use your containers, your Nvidia graphical containers that run inside Docker and are, again, this is a VM, able to leverage the power of vGPU, talk to the scheduler, and use the GPU for your applications. So in this case, instead of having your traditional applications that are CUDA enabled and use the power of a GPU, you could also use modern applications that are able to run in a Docker container and leverage the power of a GPU as well. Just you would like to do that with an application that leverages the power of a CPU and RAM instead. Right?
Makes sense. So when we talk about CUDA enabled or TensorFlow, whatever, and a vGPU profile, what is actually required to run within the VM? Is there a certain driver that is available?
Right.
What do we need to leverage the GPU?
Right. So to leverage the GPU, there is obviously the vGPU driver from Nvidia that talks to the scheduler and talks to the GPU. But you also need a license from Nvidia. So there are two types of vGPU licenses. One being your virtual app license or virtual PC license. So that's your regular VDI use. There's also the virtual app license for your RDSH, so remote desktop usage. But those two don't have the ability to run CUDA-enabled applications. And there's a third license called the Quadro VW Workstation license. And that license is enabling you to run CUDA or Tensor or any other library that is able to use the GPU from a computational perspective.
So Johan, when we are enabling VMs to use GPUs, we just explained what are the various options using frameworks and containers, but what is actually required on a vSphere level to be able to do so?
Right, so that's a good question. There's a couple of things. One being that the scheduler is a kernel module that needs to be installed obviously in the kernel. So it's a VIB package. There is a license server, and that could be either a Windows machine or a Linux machine. And there's the actual vGPU package that's installed inside the VM. So that's either this one or this one. That talks to the license server, and the license server itself will enable features that are enabled on the actual vSphere host. And there are a couple of things to check if everything is okay. So when sitting on the kernel or logging into the console, there is a tool called Nvidia SMI, and this tool will show what GPUs are in use, what frame buffer is in use, what VMs are using that, temperature, stuff like that. So this is a really important tool to make sure that everything is okay, and some of the tools that I use during implementations, also from a tweaking and tuning perspective. Cool.
All right.
Well, we explained a lot about the different architectures, the different types of applications, the architecture from a vGPU perspective. Niels, if people would like to know more about the VMware side of things and the integration between the GPUs and vSphere, where can people find that?
Okay, so we have the vSphere, the VMware vSphere blogs, and we actually have a blog series on either GPU architecture. We have a lot of information on machine learning, artificial intelligence, and what different solutions we have for that and what we support. So I would definitely encourage you to look those articles up, and there's a lot to learn.
Awesome. Okay, cool. Well, for now, I would like to thank Niels foremost for explaining everything there is about vSphere and GPUs. Thank you for watching, and see you next time.